Welcome to Cloud on Air, live webinars from Google Cloud. We're hosting webinars every Tuesday. My name is Anand Iyer. Today I will be talking about Kubeflow pipelines, an exciting new set of features that we have added to the popular open source project Kubeflow. You can ask questions anytime on the platform, and we have Googlers on standby to answer them. So let's get started. First, some introductions real quick. As I mentioned, my name is Anand Iyer, and I am a product manager in the Cloud AI platform team within Google Cloud. The Cloud AI platform provides the set of tools and services you need to build custom machine learning applications that entail building, training, and deploying your own custom machine learning models. We're also very fortunate to have Andreas Rodriguez as my co-presenter, and he will be talking about how Intel, our very close partner, has leveraged Kubeflow pipelines to build components for their OpenVINO toolkit. So first, let me present the high-level agenda of the talk. First, I'll present the motivations behind the various tools and services that we're building as part of the Cloud AI platform and provide an overview of the approach that we're taking. Next, we will do a deeper dive into the specific problems that inspired the Kubeflow pipelines initiative. After that, we'll get into the meat of the presentation, which is where I'll give you a demo of Kubeflow pipelines and also talk about pertinent technical, under-the-hood technical details pertaining to Kubeflow pipelines. And after that, I will hand it over to Andreas to talk about how Intel has leveraged Kubeflow pipelines to build components for their OpenVINO toolkit. So first, what's our motivation? What are we trying to solve as part of the Cloud AI platform? The key problem that we're trying to address is the fact that building and deploying real-life ML applications is harder and costlier than it needs to be, and that is because of lack of tooling that covers the end-to-end machine learning lifecycle, the end-to-end lifecycle for development and deployment of custom machine learning applications. And that is the key problem that we're trying to solve. Now, the next couple of slides will be a little bit of repetition for folks that attended the previous webinar, but nevertheless, I will cover this content again real quick for those that may watch this presentation later on YouTube. So when we talk to customers, customers mentioned three high-level themes, or rather when we spoke to customers, there were three high-level themes that emerged as persistent problems that hold customers back from building successful machine learning applications. The first problem was that of deployment. Today's infrastructure is brittle and opinionated, and the environments change when you go from your laptop to the cluster, and also in today's world, hybrid is a reality. The other big problem is that of talent. It's just really hard to find machine learning experts, and if every machine learning application needs a team of experts, well, that is going to be a severe bottleneck for the successful deployment of machine learning. Then the last piece was collaboration. Everyone is reinventing the wheel and implementing components, whereas the ideal state of the world is where different teams collaborate and reuse assets that they're building. So this at a high level these three problems at a high level are the problems we want to tackle. And the three pillars towards our solution are Kubeflow, reusable pipelines, and the AI Hub. Kubeflow is a popular open source project, and Kubeflow aims to simplify the end-to-end machine learning lifecycle. It provides a set of services and libraries that are seamlessly integrated that address the needs of the various stages of a machine learning application. Kubeflow is a collection of services that runs on the Kubernetes execution engine, and we chose Kubernetes because Kubernetes is effectively the de facto for deploying applications that leverage a cluster of machines. So by leveraging Kubernetes, we're able to effectively provide a hybrid solution because Kubernetes is the de facto platform on-premise as well as on multiple clouds. So by building something that works on Kubernetes, we're able to provide the Kubeflow enables customers to move their applications from on-premise to the clouds and so forth. Couple more key aspects of Kubeflow. It is an open source library that supports multiple machine learning frameworks. It is not limited to TensorFlow. It supports scikit-learn, XGBoost, PyTorch, and multiple other frameworks. And because it's open source, we work with the community to assimilate newer frameworks that become popular. One more key thing to highlight is the fact that while Kubeflow is open source, if you deploy Kubeflow on GCP, particularly on Google's Kubernetes engine, GKE, we have built some integrations that make it very seamless to deploy Kubeflow. And also for the most popular Kubeflow services, you can leverage fully managed equivalents on Google Cloud. So you don't always have to manage your infrastructure. The other aspect is reusable pipelines. And over here, the Lego analogy is very apt. We want to get to a world where components and pipelines built by others can seamlessly be reused. We don't want people to reinvent the wheel all the time. And this is particularly important because in today's world, every machine learning application is considered to be a bespoke application. So whenever someone's building a custom machine learning application, the first thing they need is a data scientist or a machine learning engineer that is focused on that application and will build a bespoke solution. But that is not always the case. Often what you need to do is actually look at other successful applications and reuse the stuff they've built and tweak the components that you need to tweak. And that is what we want to enable. And then the third aspect is the AI Hub. The AI Hub, you can think of it as a one-stop shop or a one-stop catalog for machine learning content. And I use the word content because we will have multiple different types of assets. We will clearly have pipelines built with Kubeflow pipelines infrastructure. We'll also have reusable components that you can leverage as a part of Kubeflow pipelines. But we'll also have other assets like pre-trained models or embeddings or even just notebooks where a particular model is being trained. So long story short, AI Hub becomes your one-stop shop to find assets that you can either reuse or use as inspiration to build your own custom applications. All right, so with that, now let's do a deeper dive into the specific problems that inspired the Kubeflow Pipelines project. So the key premise here is the fact that in addition to the actual machine learning, and what I mean by the actual ML, we're talking about the code that trains the model or does inference with the model. In addition to that, there are multiple other phases that you actually have to implement and manage for a successful end-to-end machine learning application. There's data integration, data collection, feature engineering, data validation, model deployment, and then tooling to capture metrics and orchestrate all these pieces together. And that can often get non-trivial. And that is a core problem that we want to solve. Let me also present a few customer quotes that will make things more tangible. One customer that we spoke to said that they don't really have an ML workflow today. What they've basically done is taken workflows that they've used for general software development and applied that in the machine learning context, but that lacks the things that ML needs. And that is one problem we want to solve. The other problem is we spoke to customers where they don't retrain their models on a frequent basis, despite the fact that model freshness was actually important for their business. And part of the reason they don't retrain models as often is because the retraining process was very manual. But we wanted to solve that problem and make it very easy for customers to set up constant or retraining pipelines that can be scheduled to run on a periodic basis so that they can get newer, updated models more easily. A third customer that we spoke to basically said ML experimentation is like the Wild West today. Everyone is using ad hoc tools. There is no standardization. It's very hard to go back and understand what led to the production of a particular model. It's hard to know what techniques have been tried, what experiments have been run, and so on and so forth. And we want to solve that. We want to make it easy for you to have one place where you can track all the experiments that were done. So with that, let me dive into the demo section where we'll cover pertinent aspects of the Kubeflow Pipelines project. Before we dive in, I want to talk about the three feature buckets into which the capabilities of Kubeflow Pipelines can be classified. The three buckets are machine learning workflow orchestration, rapid reliable experimentation, and sharing, reuse, and composability. So the Kubeflow Pipelines project at a very high level is solving problems that fall under these three buckets. So first, let me talk about ML workflow orchestration. Because we've been talking about multi-step machine learning pipelines, let me make things more concrete by first presenting a visual depiction of a pipeline that has been executed on the Kubeflow Pipelines framework. So this is the Kubeflow Pipelines console depicting an actual pipeline that was executed. Now in this particular case, this pipeline starts with a validation step where incoming data is analyzed to make sure that there are no data quality issues. After that, there is a pre-processing step followed by a training step. And then the model that's produced in the training step in one scenario is used for doing prediction on offline data. In another scenario, the same model is being deployed to a serving endpoint. And then there's a third process where the model is being used to do deeper analysis on the validation data set. Now, this is just an illustrative pipeline, and you can build multiple different configurations of pipelines with this framework. A few key things to highlight here are in addition to the visual depiction of the stages of the pipeline, which makes it very easy for you to come in and understand what that pipeline is doing. In addition to this visual depiction, you actually get a whole set of rich information required to understand at sufficient detail what was happening when this pipeline was executed. So you can see all the configuration parameters and all the input parameters that were provided to the pipeline. For each step of the pipeline, you can drill deep and select a particular step and then see the inputs and outputs of that individual step. So the inputs that were provided, what were the outputs that were produced. You can also look at logs that were produced so that you can debug things when they fail or get a deeper understanding of what happened when that step was run. What is particularly compelling is certain steps will produce interesting data that can be visualized. So for example, if you're doing analysis, and in this particular case, the analysis step was implemented using the TensorFlow model analysis component that's part of the TFX library, it produces a rich set of artifacts that can be visualized with this slice and dice UI. And the visualization of the metrics is embedded right here in the console. So for the metrics that are produced, you can visualize them right here. So in this particular case, you can do slicing and dicing of the metrics produced by that model. Let's take another example. If I go to the prediction step, I can visualize the output, which is tabular output, where each offline data set and the corresponding score assigned to it can be visualized. And if I go to the training step, for example, I can, by the click of a button, open the TensorBoard instance where I can now get a deeper understanding of what happened when that model was trained. So long story short, a lot of rich visual information is readily available at your fingertips so that you can understand what happened when a pipeline was run. So let me go back and cover some pertinent details about how what constitutes a pipeline and exactly what are the pieces that define a Kubeflow pipeline. In its simplest form, a Kubeflow pipeline is a set of containerized machine learning tasks. The reason we chose containers is because containers are the industry standard for portability, repeatability, and encapsulation. And of course, we want you to go from prototyping to production as quickly as possible, and thus containerizing your steps enables that. We also wanted repeatability and reliability, and again, containers are the industry standard solution for that, and that's why we did not want to reinvent that, and we leverage containers. But that being said, even though a single task, each step of the pipeline is a containerized task, that doesn't mean it has to run on a single node. A given task can run in distributed fashion. It can be a model that's trained in distributed fashion. It can be an Apache Spark step, which is doing distributed data processing, or an Apache Beam step that's doing distributed data processing. The key thing I want to highlight is even though a given step is encapsulated as a container, when it's actually deployed on the Kubernetes cluster, it can run on multiple worker nodes. So it can run in distributed fashion. Another thing worth highlighting is the different steps of the pipeline can use different hardware. So you can have the training step, which needs GPUs, and then the pre-processing steps probably just need a high memory CPU machine, high memory machine for distributed processing. But the key thing is different steps of the pipeline can leverage different forms of hardware, and it's very easy for you to specify what hardware is required. A third thing I want to highlight is the fact that even though a step of the pipeline is executed as a container, these containerized steps can easily invoke cloud-native services that are running elsewhere. So for example, you can have a containerized step that is calling cloud machine learning APIs, or you can have a containerized step that is calling out to other fully managed services like BigQuery or Cloud Machine Learning Engine or Dataflow. So that's a core part of what a Kubeflow pipeline is. It's a set of containers that encapsulate machine learning tasks. The other part of it is specifying the higher level workflow, specifying the sequence in which these tasks need to be run. And to do that, we provide a very intuitive Python SDK that I'll demo in a few seconds. Then the third piece that constitutes a pipeline are the set of parameters that the user has to pass in. So when we say a Kubeflow pipeline, that essentially constitutes the containers for the individual steps, the higher level workflow definition, and the parameters that the user has to pass in. So with that, let's go back and take a look at how a Kubeflow pipeline is authored. So as I mentioned, we provided a very intuitive Python SDK. And time and again, when we spoke to our customers, everyone said Python is their lingua franca. So essentially, we decided to provide a very Pythonic SDK that will feel intuitive to our audience. And this Python SDK can, for example, be invoked from an IDE or even from a notebook. And because authoring machine learning components from notebooks is popular these days, I'll actually demo usage of the Kubeflow Pipelines SDK from a notebook. So when it comes to authoring a pipeline, there are two distinct phases. One is defining the higher level workflow, and then the other is defining the individual components. And first, let me start with the higher level workflow. And what I mean by the high level workflow is the definition of the sequence in which these steps need to be executed. So to define the workflow, essentially authoring the workflow is as intuitive as authoring a Python function. You essentially define a Python function that encapsulates your workflow, and then you annotate that with a function decorator that essentially signifies that this is a Kubeflow pipeline definition. For your function, you will provide arguments, which are essentially the inputs that an end user needs to provide while running the pipeline. And you can even annotate these arguments with, 1 second, let me find the cursor. I seem to have lost the cursor. Oh, there we go. So the arguments can be annotated so that you can specify a name for each argument and also specify a default value. And we'll come back to why that is very useful and significant. So long story short, you define a Python function, you specify arguments, these are the inputs to the function, and then you start specifying the different steps of the pipeline and how they're hooked together. Each step of the pipeline is invoked like a Python function. Now at this point, you're wondering, wait a minute, each step of the pipeline is a containerized step. How did it become a Python function? Just hold on to that thought, and I'll answer that question in a few minutes. But for now, assume that each step of the pipeline is encapsulated as a Python function. So to specify the workflow, it's as easy as calling the corresponding function, providing the inputs that that function requires, and then the sequence in which the different steps need to be executed is specified by connecting the output of one function and providing that as the input to a downstream function. So in this particular case, the first function, the first step of the pipeline produces some output, which is pre-processed output. And then the pre-processed output is provided as input to the training step. And that's how you specify the sequence in which the steps need to be run. So that was specifying the workflow orchestration. Well, actually, and before we move on, I should mention that after you've defined this function, we give you simple, the SDK gives you simple operations where you can compile this higher level workflow definition into a tar.gz file that can be uploaded to the pipeline's backend, or you can also just use our client API to submit the pipeline to the Kubeflow pipeline's backend. And once it's uploaded to the pipeline system, any user can come in, pick that pipeline, and execute it. And actually, let me depict that over here. So let's say you go in, you want to create a new run. So you open this, create a new run by specifying a pipeline. And then, as soon as you specify a pipeline, you give it a name, demo run. And then you actually have this form that is automatically populated, which specifies the inputs that you need to provide to this pipeline. I mean, this is where the annotations to the function arguments were important. So the annotations specify the names of each input, and the annotations also specify the default values for these inputs. So all you had to do was author that pipeline, specify the pipeline as a function, specify your function arguments and annotate them, and that automatically becomes this easy to consume form that someone can use when they want to execute the pipeline. And this is important because often the author of the pipeline is not going to be the one that executes the pipeline. In many cases, the author is going to execute the pipeline, but we want to get to a world where the author of the pipeline can give a pre-built pipeline to others to go and execute. So I can come in, not know too many details about how a particular pipeline works under the hood, but I can come in, I can see what inputs are required, type them into this form, and execute the pipeline. It's as easy as that. All right, going back to the notebook here, now let's talk about how the different steps of the pipeline are specified. Now, as I mentioned, each step of the pipeline is a containerized step. So in its most basic and most flexible form, all you have to do is, once you have your container, so let's take this example here where I've built a container that encapsulates one step of my pipeline. I can take this container and I basically wrap it with a Python function where I invoke this operation called the container op. So this container op, which is part of the Kubeflow Pipelines SDK, takes as input the container that encapsulates the step. And also, it takes as input the various parameters that need to be passed in by the end user. And this container op takes care of invoking that container and passing it the corresponding parameters. Now, often each container has its own default entry point, and often by default that's the entry point that's executed. But sometimes containers can have multiple different entry points, and you can override the entry point that needs to be invoked by using a command called it's called command. You can specify that inside the container op and then specify which entry point has to be used for a container. So long story short, once you have encapsulated your pipeline as a container, all you have to do is wrap it with this container op, and we make it, and this produces essentially a Python function version of this operation that you can then use when you're defining your workflow. Now at this point you're wondering, hey, wait a minute, does that mean every step that I author, every step of the pipeline needs to be built as a container? That is not the case. I actually wanted to start with the most flexible method of defining pipeline steps, because anything that can be put in a container is fair game. It can be C++ code, R scripts, and what have you. But often you will not, as an end user, have to build the containers yourself. You can actually go in and just author steps of a pipeline as a simple Python function. And then after you've authored the function, annotate that function with specific function decorators that help encapsulate that function as a step of the pipeline. And when you do so, when you specify the function decorators, all you have to do is specify a base image, a base Docker image that is used to package that step of the pipeline. Often, you can get base Docker images by going to Docker Hub. For example, if you're training a TensorFlow pipeline, the TensorFlow community provides a bunch of pre-built Docker containers that are available on Docker Hub with various versions of TensorFlow and common utilities. And you can just simply reuse those containers. Or if you're working in a large organization, you may have your internal Docker Hub. But in many cases, a pre-built container may not have the various libraries that you specifically need. And again, we have you covered over there. So all you have to do is use this notebook magic that we've provided, where you specify the base container that you want to use. So in this particular case, I'm going to use a TensorFlow base container. And then after that, simply pip install the other dependencies that you need. And of course, if you're, folks that use Python are very comfortable with pip installs. You don't need to know the details of Docker, Dockerization. All you have to do is use this notebook magic, specify a base container, and then specify the other dependencies that need to be packaged into that base container. And we automatically produce a container that you can use as the step of the pipeline. And it'll have your custom dependencies. So long story short, you don't have to be an expert to author each individual step, an expert in Docker to author each individual step of the pipeline. We give you the utilities that you need to simplify the authoring of the various steps. All right, so that was authoring of machine learning pipelines. Now let's go back and look at the other key value proposition of Kubeflow pipelines, which is rapid, reliable experimentation. And this is important because machine learning, particularly applied machine learning, when you're building machine learning applications, it's all about trying many different techniques. The more techniques you can try, higher your likelihood of success. And that is what we want to enable. We want to make it very easy for you to simply author an initial pipeline, clone that pipeline, edit it to try some variant of that pipeline, and then submit it. And keep doing this loop very quickly so you can try multiple different variants. And of course, for each pipeline that you've submitted, you can view those pipelines in the Kubeflow Pipelines console. So you could have thousands of executions. You can go in and you can see rich information about each execution. What is particularly compelling is, as I mentioned, we want to make it easy for you to try variants of your pipeline by simply cloning it, editing it, and submitting it. And let me actually demo that. So take an existing pipeline, hit the clone button, and that opens up this web form that you can now tweak. You can update the parameters that go in, and then you can submit that cloned variant of the pipeline. And you can do this ad nauseum. And pretty soon, we'll actually add capabilities where you can clone a pipeline, see a version of the code, tweak the code, and submit. So long story short, try multiple different variants to see what works best. Now, for each variant of your pipeline, you can actually see rich metrics produced by that pipeline quickly. So you can identify the ones that worked well. And then you can select, say, a subset of the pipelines. Let's just say you want to do some comparisons. Let me go in here. Because often when you've launched multiple variants of a pipeline, you want to go in and compare them to see what was different about them. So I can select a subset of pipelines and hit the Compare Runs button, and I get this rich UI where I get rich information, the metrics, config parameters, and so forth, of those executions side by side, so I can easily analyze them and figure out what was different about each execution. And what is particularly compelling, and I find that this feature very interesting, if you've done training where you produce metrics that can be visualized by TensorBoard for the various experiments that you selected, with one click, you can open a TensorBoard instance where all the metrics from those different experiments are plotted in the same set of plots, so you can do rich analysis of your experiments. And then the last piece is reusability. Reusability of pipelines and components. So let me quickly depict that. So let's just say you've authored a multi-step pipeline. In this particular case, you have a 6-step pipeline. Not every step of the pipeline has to be authored by you. In many cases, you will find existing components from, say, the AI Hub that you can reuse as a part of your pipeline. Another example is where you might have an existing pipeline and you just want to swap one step of the pipeline with a different step. So let's just say you have a pipeline that uses scikit-learn to do some training, and then you soon realize that in the AI Hub, there is a TensorFlow-based implementation that might just work great for your use case. Well, fantastic. Just simply swap the training component of a pipeline, and now you have a new variant that you can try. So that's how Kubeflow Pipelines helps you go from prototyping to production real quick. And with that, I'd like to introduce Andreas Rodriguez to talk about how you can use OpenVino to get the most out of your Kubeflow pipelines.
Thanks, Anand, for introducing the Kubeflow pipelines. Before I proceed, I encourage you to continue typing your questions, and there are Google and Intel engineers answering them. Intel and Google are partnering to enhance the Kubeflow pipelines. As a first step, Intel added the OpenVino toolkit as containers to the Kubeflow pipelines. To start, I want to motivate the reason for the OpenVino toolkit, then give a brief overview of OpenVino, and then share how OpenVino can be used with the Kubeflow pipelines. Intel provides a diversity of hardware that can be used for artificial intelligence. Each one has different strengths, such as better throughput, better latency, or better power, or better memory, or better cost, or better generality, depending on the specific application. Intel's AI hardware products includes the various types of CPUs for both data center and client, GPUs, VPUs or visual processing units, FPGAs, and NNPs or neural network processor accelerators. Given the hardware diversity, Intel developed a unified API and software toolkit that can be used for inference across all the various hardware products. This software tool is known as OpenVINO, which stands for Open Visual Inference and Neural Net Optimization. OpenVINO has three main components: the Deep Learning Deployment Toolkit, or DLDT, an OpenCV and Media SDK used for traditional vision and video processing, and a collection of pre-trained models and tutorials. At a high level, OpenVINO provides a unified programming model across various hardware, is optimized for performance and memory footprint, is extendable for custom workloads, provides broad operating system support, is self-contained for a simple out-of-the-box experience, and is open source for the community to enhance and contribute. The main component that we will focus in this presentation is DLDT, Intel's Deep Learning Deployment Toolkit. It offers a model optimizer and an inference engine for optimal inference across various Intel's hardware products. The Deep Learning Deployment Toolkit, or DLDT, is easy to use and provides high performance across Intel's hardware products. Before using DLDT, you first need to train a model. You can train a model using one of the many popular deep learning frameworks on your hardware of choice. If you're training on Intel Xeon processors, use the Intel MKL DNA library to accelerate your training. DLDT has two steps. First, DLDT provides an optimized intermediate representation, or IR, over the model's graph. This includes optimizations such as layer fusions or quantization. Second, this IR is then consumed by the inference engine, optimized across various hardware products. On the left, in this slide, you can see a list of currently supported layers. Intel continues to expand this list. If a given layer is not currently supported, documentation is provided detailing how a user can add new primitives or layers, or how to further optimize existing layers. A feature of DLDT is heterogeneous execution, or the ability to execute a model across various hardware products. In this example, there is a primitive of a model not supported or optimized for FPGA that is scheduled to execute on the CPU. Another feature is asynchronous execution to hide data transfers. That is, as one inference cycle is executed, OpenVINO fetches the data for the next inference cycle. Once you have your optimized intermediate representation, using the DLDT inference engine is as simple as these 5 lines of code. Note that in the third line of code that's highlighted, the user can select from multiple hardware products. This enables the user to quickly compare performance across various hardware products to determine which one may be the most suitable for a particular model. Intel has been working with several customers to enable them to do AI on Intel's hardware products. Here are a few examples of customers we've worked with and their testimonials. GE, for example, observed a 14 times performance improvement using the OpenVINO toolkit for their task of inference across X-ray imagery. Several other customers report up to 2 orders of magnitude performance gains on Intel Xeon processors using Intel's optimizations. Intel and Google are partnering to bring the performance and ease of use of OpenVINO to the masses by adding DLDT containers to the Kubeflow pipelines. Let's review the Kubeflow pipeline via a hypothetical example. Suppose you're a data scientist at a medical AI company examining X-rays to detect cancerous cells. There are various containers to facilitate your work. The data ingestion, data transformation, and data validation containers facilitate reading data, transforming the data to the expected format, and validating that the X-ray data is usable and properly labeled. This data is passed to the trainer container. The output in this hypothetical example is a trained cancer detection model that is passed to the model validation container to ensure the model is ready for deployment or serving. The trained model is then used for serving by your medical company to examine patients' X-rays. The DLDT model optimizer takes the trained model and passes it to and gets an optimized intermediate representation, which gets passed to the DLDT inference engine for high performance across the various hardware backends. Note that not all the trained containers are needed to use the DLDT containers. The DLDT model optimizer can use an existing trained model. We have only provided a high-level overview. We invite you to try the Kubeflow pipelines with OpenVINO containers. In the links provided, we offer 2 simple examples for each of the DLDT containers to help you get started. And you can learn more about the benefits of OpenVINO using the link at the bottom. Stay tuned now for live Q&A. We will be back in less than a minute.
Looks like we have a question from the audience. What are the advantages of the OpenVINO toolkit over other serving solutions? Andres, all yours.
Yeah, thanks, Anand. OpenVINO is optimized by Intel for optimal performance across Intel's hardware backends. However, we're working to extend these benefits to other inference engines. For example, we're working to more tightly couple some of the benefits of OpenVINO with TensorFlow serving, so that TensorFlow serving can also have the same or very similar performance gains and ease of use that we can get with OpenVINO for Intel's hardware.
All right, stay tuned now for the next session, CETV, introducing Cloud TPU Pod, 11.5 petaflop supercomputer for deep learning. Thank you.